Good afternoon, everyone. This is the Jasmine Ballroom, and we're in here for Adaptive Kernel Live Patching, an open collaborative effort to ameliorate Android end-day root exploits. Before we begin, a few notes. The business hall is located in Bayside AB during the day, and the welcome reception is from 5:30 to 7 tonight. Black Hat Arsenal is on the Palm Foyer on level 3. Join us for the Pony Awards in Mandalay Bay BCD at 6:30. And thank everyone to put their phones on vibrate during the presentation. So without further ado, Yulong Zhang Tao Wei.
Thank you, and thank you for the introduction. Good afternoon, ladies and gentlemen. I'm Tao, and this is Yulong. Today we will present our work on adaptive kernel live matching for Android. Today I will discuss the problem and the challenges, and then Yulong will provide a solution and discuss about the future. First, let me introduce a little background for the people not in the system security area. The kernel vulnerabilities are one of the most important threats for Android users. By exploit those kernel vulnerabilities, attackers can get sensitive information from the kernel or escalate the privilege to root the phone. After rooting the phone, attackers can break most of the security mechanisms for Android, such as access control, payment security, key store, and so on. The Android ecosystem, to mitigate this challenge, Android ecosystem deploy a trust zone. However, even trust zone will also be threatened after being rooted, because the trust zone cannot validate the kernel inputs, cannot validate the kernel input sources. Hence, the trust zone cannot tell the difference between the benign inputs or malicious inputs, so that attackers can try to provide some fake inputs to make the trust zone to make wrong decisions. So today the only way to mitigate these changes is to put all those dirty works in the trust zone itself, such as UI or networking and so on. But this solution will increase the attacker service in trust zone dramatically, and it will introduce more and more vulnerabilities in trust zone itself. So it is a hard work. This is a graph for monthly disclosed kernel vulnerabilities. As you can see, it is increased very fast. And this growing trend is bring us one good news and one bad news. The good news is that more and more attentions are drawn to secure the kernel. But the bad news is that the on-the-ground business, they have more and more vulnerabilities to exploit. Here are the list of many vulnerabilities having public available exploits. Exploits itself is nurtured, is not bad or malicious, but there are many malware. They are using those exploits to do bad things, such as merge, reported by Fry, and Ghost Push, reported by CMCM, and Dog Spectres, and Hungbag reported by Blue Code. As you can see, kernel vulnerabilities for Android devices are real severe threats today. So let's ask a question. In fact, this is a very common question. Many people ask me about this question. Why is iOS more secure than Android? It's because iOS has fewer kernel vulnerabilities. This is a graph, the stats of iOS vulnerabilities and Android. As you can see, in most of the time, iOS have more kernel vulnerabilities than Android. But people still think Android is not good, not better than iOS. What's the issue? So the problem is that not Android has more vulnerabilities than iOS, but Android vulnerabilities remain unfixed over a much longer time than iOS. So what's the issue? If Apple wants to patch a vulnerability, it will be done in a very timely manner. Because Apple controls the entire supply chain, and Apple has the source code, and Apple forces one direction upgrade. You can only upgrade to the latest version. So all the iOS users will be sometimes forced to upgrade the latest version very, very soon. But for Android users, it is another story. For Android users, there are three main causes to delay the patching. The first one is about the long patching chain. And the second is about the fragmentation. And the third one is the capability mismatching. I will explain them in more detail next. The first one, the long patching chain. As you can see, there are 5 steps before the patch can be deployed. The first one is about the researchers. Most of responsible researchers will disclose the vulnerabilities to the vendors, the different vendors such as Google, Qualcomm, or the phone vendors. But there are also exploits appeared in public but never officially reported to the vendors. Last year, a CCS paper by Professor Chen reported such a phenomenon. They identified at least 10 device driver exploits never reported to vendors. The second step, after vulnerabilities reported to the hardware vendors or Google, there are still some exploits disclosed but not getting timely patches. Here is a blog by Project Zizo from Google. It disclosed that one patch was not applied to the branches after being available for 6 months. Okay, the third one is about the carriers. Sometimes phone vendor provide patches, but carriers delay or deny the patching. This is another report, and the carrier, sometimes they even decline to do the work and never release the patches. So the last step is many users delay the OTA due to the rebooting. So there are issues in every step. Okay, the second challenge is fragmentation. Here is the graph for the Android fragmentation. It's very, very, severe for vendor itself or for security researchers. To simplify, we can see a much simpler problem is that the version fragmentation. As you can see, there are still a lot of old versions in the real-world devices today. And in some local markets, it is even worse. This is stats for Chinese markets. There are still more than 40% of devices are older than 4.4. Okay, the third one is the capability mismatching. In fact, phone vendors have the best position to patch those vulnerabilities. However, they are most of the time they don't have enough resource to discover and patch those vulnerabilities, especially after 1 year or 1.5 years. The original developing team are not using this anymore. So no one cares about the old phones. But for the security vendors, they are capable to do those security work, and they want to join the first to protect the users. However, they are not privileged enough, and without source code, and it is very hard for them to handle all those fragmentations. So today, the situation is that the phone vendors don't have enough resource, and the security vendors don't have the privileges, and Google have tried his best. Okay, let's do some case studies. This one, Tao root, is very, very famous for Android area. It is disclosed 2 years ago, and ping-pong root is disclosed 1 year ago, and the 1805 is disclosed this year. As you can see, the Tao root has been disclosed, almost 800 days. Yeah, so, but there are still more than 20% device can be rooted by Tao root. So this is very severe. Okay, so we are facing such severe changes. So how can we secure them, all the pay systems? In fact, all the security teams from different vendors, from software vendors, from phone vendors, from Google, we are working hard to secure the Android ecosystem. But due to the fundamental issue, because attackers can get the root bridge very easily, so it is very, very hard for us to do this work very in a efficient way. Okay, that you want to introduce the solution.
Thanks. So as Lance just said, the situation is quite bad. So we propose two solutions to tackle this problem. We call them Adapt K patch, and another one is Lua K patch, which is even better. Essentially, they are kernel level patching, but we do more than kernel level patching. We can do auto-adaption. So kernel level patching is not a new idea. So we can see there have been a lot of solutions out there for many years, like K-patch for Red Hat, K-graft, K-splice. I think it's from SUSE. And even Linux upstream has the live patching mechanism, which is called live patch. So to use K-graft as an example, so in the kernel, if there is a vulnerable function, they will use a new function to replace the old one and hook the invocations towards the new one. And this way, the invocations to the buggy function will instead calling to the fixed function. So all of the current live patching mechanisms follow this algorithm. So first, they will load new function into the memory and make it accessible by the other kernel code. And then it will do the safety check. Sometimes it will try to stop the world and see whether the stack contains the old function. So if the stack contains the old function, it will not try to replace it because it's pretty dangerous to have two copies of the functions, one old and one new, in the same call stack. That's different context. So if they can check that there's a clean stack and no calling to the old function, they will try to replace, to hook the old function to the new function. So although we have so many choices out there, we still have some challenges that stop the world to use live patching to fix all the problems that Lance have just described. Well, the first one is that most of the existing work requires source code. So how do they achieve the live patching? They use two copies of the source code. One is vulnerable and one is fixed one. They compile two copies of the binaries and generate the diff. And they use the diff as the new function to apply to the function to the kernel. But the assumption is they have to have the kernel source code. Imagine that for a third party, if they want to patch the vulnerability, how can they access the exact copy of source code of every phone? That's challenging. Even if they have the exact source code, they cannot just apply a patch for one phone to another phone. Because if you compile kernel module, for example, for one certain phone, you cannot just load the same module to other phone the kernel build. So here's how we solve this problem. We call this new framework as Adapt K patch. Basically, we have 3 steps. The first one is to collect kernel information and prepare a patch template for each bug. And then we fill this connected kernel information into the template to generate an adapted patch. And after generating the adapted patch, we will inject the patch payload into the kernel memory for the patch work. We have 2 choices. The first one is to load a kernel module, and the second one is to write to the KMEM or MEM device. We will talk about this in detail later. And after loading this patch payload into the memory The rest of the thing is the same as other patching mechanisms, like in-place hooking, in-place modification, or hooked invocations. So let's dig into each step in detail. The first step is kernel information gathering. We collect some information, including the kernel version, the ver magic, the kernel module CRC, etc. We collect such kind of information just to make the module fit, adapted to the targeted platform. Sometimes we can collect this information from the kernel memory, and sometimes if we have enough, we have root, we can directly extract the boot image and get the kernel for analysis and obtain the information. And the second step is to inject the patching payload into the kernel memory. As we said, we have two choices. The first one is to load module into the kernel, and the second one is directly write the binary executable into the memory. We did a statistics in Chinese market and found that 95% of the devices have insmod function. And 60% of the devices have KMM device. So that's added up to 99.4% of the devices. So which means the majority of the devices can be fixed by combining these two methods. For the first choice, the kernel module injection, we will prepare a kernel module template for each bug. So for example, tower root, we have a module template to fix this vulnerability. But for this template, we leave some field as blank that should be filled in later when we do the adaptation. So some fields include the ver magic, the symbol CRC, and etc. So here is an example of the header of the kernel module. So we will prepare the empty buffer and later fill the collected information into the module. So after we do this adjustment, the kernel module can be loaded into the target platform. But that's not the end of the story. On some platforms, there are further check. For example, on Samsung devices, they will check whether the module has been properly signed by Samsung's private key. So in that case, if you want to load adjusted kernel module, we have to pass the kernel to just not validate the kernel signature. But after loading our patching module, we have to patch it back for security reason. The second choice is to do the MEM or KMEM injection. So that's similar. We prepare a struct that has empty fields as a template. And after collecting enough kernel information, we fill such information into the template. And then we can do the binary executable injection to execute it on the target platform. So in this way, if there is any dependency in the code, it can be automatically solved. For example, if it has to call VM allo symbol, we can just search the symbol and fill this into the structure. So after these two choices, we can adapt the patch and inject it into the memory. And then we can do the same thing as other kernel live patching choices. For example, we can override the kernel function pointer to redirect the invocations to the new function. Or we can just override the patch code directly in place. And also we can do like inline hook to change the invocation to the new function. Overall, our procedure looks like this. For each vulnerability, we have a patch template. And after we collect the target device information, we can adjust the template into an adapted patch. With this adapted patch, we can load it into the target platform and do the patching work. So the challenges we described earlier can be well solved. So for example, we don't need source code anymore. We just prepare a template, binary template, and then we can collect the needed information for you, and it will fill the information for you, so you have an adapted patch afterwards. And in this way, you don't have to worry about like adaptation anymore. Like you can generate a template for one device, and we can do the adaptation for you. You can load it directly into other devices. So imagine that right now the pie chart looks like the left one. with our adapted kernel nav patching work, it can looks like the right one. We have successfully evaluated this framework on many existing famous CVEs. So we listed here, and you can see that many of the famous routes can be tackled, like Farmer route, Tower route, Ping Pong route, and the recent 1805 pipe route. We have tested this framework on many famous platforms, like Samsung devices, Huawei devices, HTC devices, Lenovo ones. And in fact, we have tested on almost all the well-known vendors. If you have the phone that's not listed on these slides, you can contact us. And here is a quick demo. So we got a cool pad Android phone here, which is one of the famous Chinese Android phones. So sorry for the Chinese encodings. The user is trying to see what's the version number of this phone. It displays as Android 4.4.4, which is quite old device. Of course, it has many vulnerabilities that can be exploited to get root. And we use the King root, one of the top root vendors in China, to root the phone. So it tried to scan the phone for vulnerabilities. And it found that the phone is rootable right now. And actually, it tried to root the phone using ping pong root. And you can see that it successfully rooted the phone. For comparison, we undo the root by uninstall this app and reboot the device. After rebooting, we will use Baidu's live patching framework that we just described to fix the vulnerabilities. So you can see right now we launched the Baidu kernel adaptive live patching framework, and it scans how many vulnerabilities exist on the device. And you can see that there are 5 kernel vulnerabilities exist right now. So we do the one-click fixing. And you can see that all the vulnerabilities have been fixed. So right now, if we install the King root again and do the root work, it should fail because there's no exploitable vulnerabilities anymore. Here is, again, it scans for exploitable vulnerabilities. It will eventually fail after all the attempts. You may think this is slow, but we have actually fast-forwarded. It actually tries a long time, try to find all the possible root exploits. And then it draws the conclusion that it cannot be rooted. So here, this is the demo that we fixed the vulnerabilities use adapt K patch. But this solution can be further improved. Recall the 2 problems, the long patching chain, which we have already solved. Because after researchers found the vulnerability, it does not require the long patching chain to be go over to get the patch delivered to the device. We can use this framework, adapt K patch, to quickly deliver the patches to the target phones. But there's still another problem that is unsolved. This is the capability mismatching. Right now, as I just said, we have to first gain root in order to collect some kernel information and in order to load the kernel module or to inject the binary code into the memory. So we have to exploit the vulnerabilities first in order to fix the vulnerabilities. So that's an unstable solution because if you try to root in the first place, you may crash the phone. So what if the vendor can cooperate with us? So here's the scheme where the phone vendors and the security vendors can work together to integrate the adapt K-patch framework. So the vendor can pre-integrate the patching module into the kernel space. And in kernel space, the agent can do patch verification and auto-adaption, patch execution, and even some failover mechanism. For example, it can monitor the work of the hot patches. If it causes instability, it can undo the hot patches. There's still another issue is the security of the patches. So we are proposing a framework where others can help the vendor to patch. But why should the vendor trust other vendors? For example, why Samsung should trust another security vendor? So we should have a patch qualification and vetting process above this framework. So first, we should do vendor qualification. In order to form this joint effort, one vendor must to pass the vendor qualification process to join this cooperation. And the second step is after you submit a patch, hot patch, you have to pass the security vetting of all the vendors. And third, after the deployment of the patch, the user can rate the patch, like how stable it is, whether it has backdoors, whether it can cause exploits, further exploits. Still, this is not like perfect solution. If you want to ensure the security of a binary, you have to go through a long vetting process. That takes probably weeks, so still it's not fast enough. So we are proposing another improved version of this, which is much better. We call it Lua K patch. It offers more flexibility, yet has more constraint, so that you don't have to go through the complicated reviewing process. Ideally, the mechanism should be powerful enough to block most threats. And then it should be agile enough for quick patch generation. But still, it has to be restrictive enough so that you don't have to do the strict reviewing process to confine the damages. We call it Lua K patch because right now we use Lua implemented. But as a matter of fact, you can use any type-safe language engine to implement it. A type-safe and dynamic language has the advantage that it is easy to update the patches. And it has a natural jail to confine the execution. And also, for most of the type-safe dynamic language, you don't have to worry about memory-typed vulnerabilities like Stack Overflow. We chose Lua because Lua is light, it's small, and it's fast. And also it has better integration with C, and also it has GC. Here is our design principles. Our observation is that the majority of the vulnerabilities come from the input, not enough validation on the input. So on the leftmost graph, you can see that a kernel function usually takes inputs from the arguments, or in the middle of the function, it will call a copy from user to get inputs from the user land. If it fails to validate input enough, like the middle graph shows, if a malicious input comes in and it fails to validate the input, the CFG may be hijacked. So we call this like a Pond's situation. And what if we do enough check on the input interface? We can block all such kind of malicious input. Some may argue that not all of the kernel exploits happens in this way. Some are actually race conditions, etc. But we can use the same mechanism to block them. We can detect such kind of situation in the function entry or in the middle of the function to see whether such kind of situation happens. Based on this observation, we have the following restrictions in this Lua engine, in kernel space Lua engine. So first, the patch, which is executed in the Lua engine, it can hook a target function's entry. If this is not enough, it can also hook the middle invocations where conditional code is returned. By conditional code, we mean the execution status. So for example, copy from user, it will return a true or false condition to indicate whether the execution is succeed or not. And in the first and second condition, the patch can read anything that can be read, like registers, stacks, heaps, and code space, etc. As long as it doesn't reach the invalid memory space to trigger the memory fault. But in the fourth rule, we forbid any write, so no write by the patches. It cannot send data out as well. After judging based on the read inputs, it can return error code, like this is malicious or not. To get a more concrete understanding, we use an example here. So the function called fun, it calls two functions called foo and bar. Foo function returns the execution code, status code. If it is failed, it will return invalid, status code. So in this kind of situation, we call foo is a satisfied sub-invocations. So we allow the patch to hook foo. But for bar, we don't allow the patch to hook it because the return value is not used as a conditional check. It's used as the callback invocation. Based on the aforementioned algorithm, we implement the Lua K patch based on the Lua engine. It's roughly 11K thousand of code, and 600 lines of code are the core patching logic. After compiling it, we got a 800 KB kernel module, which is quite small. We can just load it ahead of time by integrating it into the vendor's firmware, or we can root the phone by load this afterwards. We provide the following capability interfaces. The first one is a symbol searching. You give a symbol to it, it can search the address of the symbol. And after it gets the address of the symbol, you can hook the address. And you can do type the reading by read any memory space with the type. And also we feed thread information into the patch so that it can see which thread it is in. Here is an example of the patch. So the kpatcher function, Lua function, is a callback that will be called after the target function executes in the hook point. And in the 14th line, you can see that we search the symbol fulltext_q, which is a tower root vulnerable function. And in the last line, it tries to hook this function. In this case, if fulltext_q is executed, it will call back to the kpatcher handler. The kpatcher handler will try to judge from the registers from the stack. In this case, it is the two parameters. One is called uaddress1, the other one is uaddress2. It will check whether the two parameters are equal. If they're equal, it is a tower root exploit condition. Then it will return an error. Our framework, after our framework see this error returning, we will know that there is an exploit condition. We will not execute it into the fulltext_q function by trigger the exploit. We will just return the error code for fulltext_q, just like it fails to execute. We tested this framework on many CVEs as well. So you can see that almost all the famous CVEs have been tested through. Some are easy to defend against. They can just put a check on the function entry. But others need to also hook the middle invocation of the function, like the highlighted ones. Usually the middle hooked invocations are copied from user. But you can see that most of them are easy to be fixed just by checking on the function entry. We can give two examples. The first one is the CVE 2013-1763. This is the source code of the patch. We can just do the function entry check to achieve the same check, to achieve the same validation. And the second example is CVE 2013-6123. So this situation is quite complicated. You can see that from the right-hand side patch, it has to rely a check on something that is obtained from the user space. So this is the second type of the fix that we just described. So we have to hook the copy from user to check the input from the user space as well. So here is another quick demo to show this kind of solution. So we use Dual Mobile, another security vendor's tool called X-Ray on Android, to scan the vulnerabilities on the device. So this app will actually try to exploit the phone to see how many vulnerabilities are exploitable. So here you can see that it finds that the ping pong root and tower root vulnerabilities exist on this phone. Then we launched Lua K patch. We also found the two kernel vulnerabilities. And we click the one button, Protect Me. We load the Lua function into the kernel space to do the proper check. And then we go back to the X-ray to scan the phone again. There are other vulnerabilities in user space. We didn't fix them, so you can see they're still vulnerable. But for these two kernel vulnerabilities, the ping pong root and tower root, it is no longer vulnerable. So they got properly fixed. And you can see from the process, the fixing period is actually quite short. We just click one button and bam, it just got fixed. But how fast it is, as for the normal execution, we tested performance by CF bench. So you can see that the leftmost bar is the base. It's a normal condition where no patch is loaded. And the right three bars are situations where we patch the tower root, patch the ping pong root, and patch both vulnerabilities. You can see that the performance is not impacted at all. There are these tiny deviations. That's because CF bench, the score is not stable. If you run it multiple times, it will get different score. We ran 20 times for each case and got the average, but still there is a tiny deviation. This is a reasonable result because usually the severe kernel vulnerabilities usually happens on the code path that usually you cannot reach. If you frequently reach such kind of a path, it should be detected by security researchers many years ago. But still, we're interested if we load patches on the hot code path. What if the code path that has Lua patched is frequently invoked? Here we use the syscall change mode as an example. If you just execute this syscall on Nexus 5 with Android 4.4, it takes 100.7 microseconds to finish the execution. But if we patch this syscall with Lua K patch with different kind of logic, you can do a direct return, you can do conditional comparison, you can do memory read, and you can do complicated combination of operations. But all such kind of conditions only generate below 4 microseconds overhead. So that's only 4% of a change mode syscall, which is pretty negligible. In the worst situation, we got the if we want to hook a frequently called syscall, get time of the day, this syscall will get called on the 100,000 times order on the Nexus 5 phone. Even on this extreme condition, if we hook all those invocations, it only generates under 1% overhead, so which is quite small. And furthermore, as an ongoing work, we will replace Lua engine with Lua JIT or BPF JIT. That should be even faster. So in the world, we propose the two solutions, the Adapt K patch and Lua K patch. But our ultimate goal is not only to propose the framework itself. We want to use the framework to build an ecosystem for the all the vendors to join together to fix the issues that we just described. So based on Lua K patch, the vendors can fix problems in days, probably just 1 to 2 days. And if some problem cannot be fixed by Lua K patch, because since we put a so strict rule on the patches, you can fall back to the adapt K patch. If in this case, you still have to go through the patch vetting process. So in this case, it has to take weeks to get the problem fixed. But still, it is faster than the traditional code patch. So based on the workflow that we listed in the above slides, we can got a joint effort from the overall ecosystem. So why should we have the combination of the effort? Because the kernel vulnerabilities are getting more and more complicated. So a joint effort means more and more forces can help to generate patches to tackle the vulnerabilities. And in the adapt K-patch scheme, patches can be vetted to be more secure if there's more vendors here to vet the patches. And last but most importantly, all the vendors can join together to establish a standard. So as Lance just said, we have already got a severe fragmented ecosystem of Android. We don't want to get another layer of fragmentation of patching. So suppose we propose the live patching framework here today. If different vendors implement it in different way, we can get different solutions. The patches should be deployed to fit into different kind of channels. So that's another layer of fragmentation. So we don't want that to happen. So here we call for the joint effort into this ecosystem to build a standard of hot patching. And for more details, you can refer to our white papers. And that's all about our presentation. So thanks a lot. Any questions? Yes. So there is open mic in the aisle. Yeah.
So I have a question. So this is live patching, right? Do you take care of the case when the phone has already been looted or has already been compromised in some way and modify the information that you are collecting at the first stage?
No, this is not in our threat model. Yeah, but I think our solution will help users to after removing the bad guys and protect the device. But we don't consider such an adversary now.
Okay, I cannot really hear that. It's fine.
Thank you.
I understand you're at the beginning of your journey yet, but there are certain things such as rollback protection, real-time kernel protection, integrity measurement architecture, which rely on entire setup of hashes and signatures on the image. And during an auto update, we consider this. What will happen? What do you think about it will happen when you do it in a partial patch operation? You have a roadmap for that, at least.
Sorry, can you repeat the question again?
So there are certain security mechanisms, such as integrity measurement architectures,
yes. Mm-hmm.
such as real-time kernel protection,
yes.
and so on. And when you partially update, you basically break a hash tree or a chain of security mechanisms. So what is the roadmap for these? What do you think? How could it be solved without actually generating as much time that you consume with the over-the-air update?
Okay, that's a good question. So we are actually working with other vendors on this right now. So right now, you can see that there have already been some kernel integrity dynamic protection in the kernel space, right? But they are not the silver bulletin. They are not silver bullet. So they cannot well solve the current root problems. So we cannot just rely on the integration dynamic protection. So as you said, so what if such kind of solution exists, but on one hand, they cannot tackle the problem. On the other hand, they blocks our dynamic memory modification. So in this kind of situation, we either should patch the kernel to whitelist our operations, or the vendor can cooperate to just open the interface for us to do the patching work. And of course, they have to do the authentication authorization so that only the legitimate operations are allowed.
And there's also the question of how to manage the keys for these operations, because you have to obviously sign your patch and so on, and you are dependent on the vendor again in this case. You have to give your key, or you have to take their key, and so on and so on. Doesn't it also add some overhead to the operations?
That's another good question. So right now, our design is that when the third-party vendors submit the patch, they have to sign the patches. And when the phone vendor takes the patch, they have to sign the patch. Only the patch that can be verified by both vendors can be loaded into the kernel memory to be executed. Your question is whether this generates another performance overhead, right? So first of all, kernel space already has implemented many cryptography functionalities just to do such kind of functionalities, like to verify signatures of kernel modules. So this was by design already integrated functionality. And second, we only do this on the patch loading process. It does not happen all the time. It just happens when we do load the patch. So it will not significantly hurt the user experience.
Thanks.
Thank you.
So my question is, basically you have at least 20, 25 vendors that you have to work with at the very minimum in order to do this for the majority of the devices that are out there. Right now, what percentage of those vendors are actually interested in talking to you about this? Because it fundamentally depends on them buying into it. And then what has been the biggest resistance that they've had in terms of telling you that no, they won't do this?
We just launched such a solution, and now we are called for cooperation. So we will after standardizing the framework, we will ask vendor one by one. Yeah.
Not yet approach the vendors to try to get them to participate. Understood. Okay.
Thank you.
Yeah.
Okay, I think that's all. Thank you again.